A world obsessed with better, faster, cheaper. I answer with finality, one unified design. Stormwheel V2. Sport in the stance, science in the skin. Lighter to lift, stronger to trust. More power on tap and savage to ride. Fuck, that dream again. Relentless. I can't think about anything else. The lines, the clearance, the thermal path. Every change is obvious now. Time to finish V2. Quick catch up, my first prototype, designed from scratch, built by hand. But I didn't even know what a Onewheel was. Yet the spot flowed through the streets day after day. Along the way, it wrote the upgrade list. Now it's time for the complete rebuild. New footpads, new pressure sensor, splash protection, high-end battery, complete thermal path into the frame, onboard safety system, Nylon PA6, carbon fiber, aerospace grade aluminium, every part reworked, stronger than before. Stay with me, let's dive in. Hi, my name is Leon. This part of the video is sponsored by JLCCNC. So, let's start with the main frame. This is the backbone of the whole board. Precision matters. In the last video, I built it from a paper-based composite on my hobby CNC. It worked for the prototype, but I want a board I can ride for years. So now I need real quality. That's when JLCCNC reached out to sponsor this video. Honestly, I was blown away. JLCCNC is a contract manufacturing service. They turn your 2D drawings and 3D models into parts. CNC milled aluminium, metal 3D printed components and more. They build what you design. I prepped my parts and uploaded it to their site, surprisingly easy. They even handle finishes under one roof. I chose a sandblasted black anodized finish. More scratch resistant and it looks premium. The next day a real engineer flagged a couple of issues in my drawings. Proposed fixes, readjusted, and the day after I had a firm quote. Quick disclosure, JLCCNC provided a discount of these parts, but all opinions here are my own. 5 days later the parts arrived. Clean finish, crisp edges, tight tolerances, exactly what this build needs. If you got a project and you are short on time or tooling, whether you are a maker, an engineer or business, JLCCNC has you covered. Link in the description. Easy, affordable, reliable. They ship worldwide with express options. Big thanks to JLCCNC for supporting this video. Back to the build. The main frame needs a few last touches. Countersinking the 4mm and 10mm holes, so the flathead screws sit perfectly flush. I bought brand new countersinks for this. My last cheap ones from Amazon were garbage, and these weren't cheap, but worth it. I am doing the sinks on the milling machine at low RPM with a bit of cutting oil, clearing chips with compressed air between packs. The cutters go through clean and the anodizing stays untouched. Quick debur and a wipe and we are done. Final step, cutting 28 M4 threads into the frame. I start by marking each position and center punching carefully. Then I grab a sander drill that's a bit too small. I lean in and snap. The hardened HSS tip breaks off and gets buried deep in the aluminium. Worst case. These parts come from half across the world and I've got no spare parts. So, out comes the Dremel and the diamond borer. It's slow, delicate surgery, but it works. I managed to get it out without damaging the part. Then, back to basics. Proper pilot hole and hand tap with cutting oil. Quarter turn in, half turn back to break the chips. Blow it out, test with the screw. Many hours later, deep into the night, all 28 threads are cut. Usable, clean, and the anodizing is still intact. In my last prototype I used the cheapest batteries money can buy and built an 18S2P battery pack out of them. That's 18 cells in series, giving me 75.6 volts when fully charged. And with 2 in parallel, the current doubles. How much current exactly? Hard to say. The specs were clearly fake. So to figure that out, I built this quick test setup right here. The wire has a resistance of 0.22 ohms. At 4 volts, that's a current draw of around 18 amps, something a real Onewheel battery should easily handle. The voltage instantly drops from 0.9 to 3.3 volts. That's far too weak. So, what does that mean in practice? Maybe you're climbing a hill or acceleration fast, but the battery can't deliver. The board cuts out and you nosedive face first. That's why I decided to build a new battery with high quality cells that can deliver 35 amps continuously and up to 60 amps peak. Since I'm using 2 in parallel, that's 70 amps continuous and up to 120 amps peak. Have you ever built a battery before? What was your experience like? Have you ever fallen into the trap of buying cheap cells? I would really love to hear your thoughts in the comments. Alright, let's build the batteries. To keep things short, I've heavily cut down the build and only keep the highlights. Since this is already my second battery, the process was a lot easier this time. Still, I was pretty tense. I really didn't want to mess anything up. And because building these kinds of batteries can be extremely dangerous, please don't take this video as a step-by-step guide. Think of it more as an inspiration or simply entertainment. I made these small pads from nickel strips to connect 4 cells into parallel groups. You could buy them, but I decided to make my own. I'm now welding them onto the battery so I can build the fuel series parallel pack. First, I cover the contacts with insulation paper. Then I separate the 2 blocks with a 3D printed TPU spacer. And finally, I secure everything with fiberglass tape to create a solid unit. I'm soldering the balancer wires to my custom nickel pads now. Later, these wires connect to the BMS, so it can monitor each cell pair individually. But this is where I completely messed up. I ordered solder from Amazon and it was still terrible. It just would not stick, even so the reviews were great. So I ordered another one, same disaster, and another one, still garbage. Seriously guys, do not buy cheap solder. Yes, good solder is expensive, but trust me, it is worth it. Have you had similar experience with solder? I'm printing the battery housing in PETG-CF and milling the base plate from aluminium. The aluminium plate acts as a part of the thermal mass cooling system, transferring heat from the battery into the thick 10mm aluminium frame. To improve heat transfer between the battery and the base plate, I'm adding thermal pads. Thermal pads are not the best heat conductors. Thermal paste would perform better, but it would be a total mess to work with. For the BMS connection I'm using 2 GX16 aviation connectors. Soldering them was extremely fiddle, but the setup should make future battery maintenance much easier. The main frame is done, the motor mounts are ready and the battery is finished. Now it's time to 3D print the front and rear bumpers, along with the crossbars. But before we can start printing the bumpers, I want to talk about the new design. Here you can see the old version. I didn't think it was bad, but it just wasn't round and smooth enough for my taste. Since I usually work in CAD with sheet metal, sharp edges and welds, it was actually really hard for me to create a flowing organic shape that matched my vision. So I decided to try something different. Just like they do in car design, I grabbed some clay and started sculpting my own bumper to get a better feel for the form I wanted. I designed a 3D printed frame for the bumper and used it as a base. Then I started applying clay on top and shaping it into the form I had in mind. It actually felt a bit like building dirt jumps. Oh, that's actually me. And maybe you didn't know this, but dirt jumps are often built out of clay too. Anyway, after many hours of work I finally end up with the shape I was pretty happy with. Especially considering this was my very first attempt at something like this. Then I did a quick 3D scan of the bumper with my phone. It worked, well, let's just say not great, but I still used it in CAD as a rough reference. As you can see in this quick montage, I didn't model it using fancy freeform surfaces. Instead I built it with basic CAD features, cutouts and simple geometry shapes. In my last prototype I used PETG, which is great to print and a very reliable all-round material. But this time for the final build I wanted one of the best materials when it comes to wear resistance. Pure Nylon PA6 gets really close to injection molded quality. It's incredible impact resistant, chemical stable and at the same time flexible and durable. In my opinion, Nylon PA6 with carbon can't compete here, because it's much more brittle. which isn't ideal for a bumper that has to slide over asphalt or take a hit. The problem with pure Nylon PA6, it's an absolute nightmare to print. Using my Bambolab A1 Mini, I'll show you what happens when I try to 3D print a simple rectangular piece. The warping is extreme. As you can see, it curls up like a banana reaching for the sun. To make PA6 actually printable, you have to go all in. For printing I'm using my Bambolab P1S, a sunroof filament dryer S2, a cheap glue stick and a hairdryer. I still need for my hair. Priorities, right? Oh, and a temperature sensor with a relay to switch the heat on and off automatically. And yes, I actually drilled 2 holes into my printer and cut out a bigger opening for this setup. It honestly hurt a little to do that to my Bambolab. The temperature sensor is connected to my lab power supply and the hairdryer runs through the adjustable speed controller, otherwise it would pump out way too much heat. After that I load the filament and finally I wrap the entire printer in insulation foil to save energy and keep the chamber warm so the hairdryer rarely has to kick in. Please don't copy this setup, this is not the professional way to do it. This is just me experimenting. Before starting the print I put the filament in the oven for about 10 hours to make sure it's completely dry. Then I keep it in the filament dryer to maintain the dryness. The print bed goes up to 100 degrees and I coat it generously with PA glue. Finally I load a custom print profile in the slicer. It's a brutal process, but the material is absolutely worth it. First, I printed the cross braces. Before I could take them out of the printer, I had to let everything cool down completely. Otherwise, the part could still warp even after printing. Luckily, they turned out great, which means we can move on to the tricky part, printing the bumper. This one has a print time of around 30 hours. Since I didn't want to leave the printer running unattended after all the modification I made, I think that goes without saying. Those 30 hours were tricky to manage. At first the print looked promising, but then I noticed a lot of small imperfections. Removing the support material was an absolute nightmare. And in the end the part had shrunk just enough to ruin the fit during the test assembly. I tried again with a new profile, but the results weren't much better. After 4 or 5 days and countless hours of waste, I finally gave up on printing the bumpers in pure nylon. So I decided to print the bumper in PETG carbon fiber. Sure, it's definitely not the best material for the job, but I'm curious about the comparison. Since the first prototype bumper was printed in regular PETG, I want to see how the PETG CF version performs. The print itself went perfectly. Clean, fast and without any issues. A small success, even in defeat. So the battery and motor controller can dump the heat through the bumper into the frame. I glued in front and rear aluminium plates I milled on my CNC. Last, I printed the splash guards and footpads. The guards were printed one at a time, the footpads both at once. Standing upright, I originally want them in wood, but due to their shape I went with PETG CF. Nearly 20 hours of print time, but that turned out great. The new footpads mainly consist of a base plate and a sensor plate for the front foot. To reinforce the structure, each footpad gets a CNC milled aluminium bottom plate, which I glue in place using 2-part epoxy. The glue needs to be spread evenly, and then everything gets clamped down firmly until it cures. What makes this new footpad special? The front one will have a small display built in. It shows the battery level, battery temperature and the currently selected light color. The first footpads I built actually worked great. I designed my own footpad sensor using VeloStart and custom electronics, and it performed exactly as intended. But then, one viewer mentioned that he wouldn't fully trust the material in the long run, so I thought, why not improve it anyway? That's why this version used small industrial grade pressure pads. Same principle, just a bit more robust. Since the new industrial pads are quite small, I'm using 4 of them, 2 on each side, wired in parallel. This way there's enough surface area to reliably detect pressure from any foot position. I'm placing the grip tape directly over the sensor. I cut it on my CNC using a 5W laser. 2 passes plus air assist give me a surprisingly clean cut. The grip tape I'm using here isn't quite as high quality as the one I used in my prototype. That one was from a much better brand, but this one still gets the job done. Yuki, what do you think? Is it good enough? To distinguish front and back, I designed two different headlight models, two for the front and one for the rear. I'm printing them on my resin printer using transparent resin to control how much light they let through. I tint the resin manually with an alcohol marker, that way I can fine-tune the diffusion and keep the light subtle instead of flashy. The printed headlights came out surprisingly well. The tint was strong enough to tone them down visually, but still let enough light through. After printing, I removed the supports, cleaning the parts in isopropyl alcohol and cured them under UV light. Then came the fiddly part, equipping each housing with addressable LED models, a lot of precise soldering work, but worth it. To control the LEDs and the display later inside the Onewheel, I'm using an ESP32 Mini. It's a super tiny module, perfect for tight spaces. But for the first testing, I'm using a full-size ESP32 dev board, just to make sure everything works the way I imagined. I glued the LED models into the housing using UV resin and added resistors directly to each lamp. Then I wrote a quick script to test different light bulbs, and after some debugging, it finally worked. As you can see here, I'm cycling through various patterns. This one is a secret police mode. Once everything was running smoothly, I sealed it all with hot glue to make it waterproof. Finally, all the parts are done and ready for assembly. I think you can already tell the color scheme works really well. Black on black, hard to go wrong with that, right? We start by installing the lights into the bumpers. They simply slide in from the side and stay in place through friction. Next, we assemble the main frame with the PA6 nylon cross beams using M4 countersink screws. At this point, I'm only tightening the screws loosely. Almost every screw on this board is an M4 countersunk screw. That means you can repair or maintain the entire board with just a single hex key. To ensure proper heat transfer from the bottom of the bumper to the main frame, I used thermal paste from the computer hardware world. I spread it carefully along the sides to maximize the contact surface. Unfortunately, it's a bit of a messy job, and keeping everything clean during the process was not exactly easy. The first parts fit together surprisingly well, which is not something you can always accept with Nylon PA6 crossbars. Next, I prepare the motor controller and upgraded it with new connectors. That will be easier to service in the future. For the wiring harness, I already included dedicated pass-throughs in the crossbar design, allowing the cables to run cleanly from front to back. The motor controller is mounted on a custom ABS printed plate. To ensure good thermal transfer to the aluminium base plate, I applied thermal paste again and use a custom brass heatsink to carry the heat away efficiently. The same applies to the battery. Its enclosure has an aluminium button plate that touch the aluminium bumper using thermal pads. The bumper in turn makes contacts with the main frame, creating a thermal path for heat to dissipate. After that, I can mount the battery and connect the BMS wires. To mount the motor to the main frame, I'm using two aluminium blocks, one on each side of the motor. These are bolted directly to the motor and then fixed to the main frame using two M8 countersunk screws each, creating a solid connection. What do you think of my custom motor mount? Too complicated, or would you have done it completely different? Now that the motor is mounted, I can finally route the cables properly. I'm trimming them to the right length, securing all the connectors and adding extra insulation to the critical ones for safety. If you're interested in the electronics side of things, check out the first video in my Onewheel series. I go into more detail about the electronics there. Now I can mount the footpads and for the first time install the splash guards. And they fit perfectly, down to the millimeter. There's a tiny gap, but I think it should be just fine. To squeeze a few extra kilowatts out of the board, I created custom stickers for metallic foil. Laser cut, of course. I'm hoping to achieve a refined look here, not some cheap tribal decal vibe. In the end, these graphics should add a bit more visual dynamics to the wool board. Would you have gone with a different color for the decals? Or maybe create a complete different design? Something a bit more bold and eye-catching? Finally, the board is fully assembled. It runs flawlessly. No rattles, no weird noises, and I'm honestly really proud of how it looks. This project is built on so much hard work, especially failure after failure after failure. But after pushing through all of it, this is the result. We are just a moment away from the very first test ride. Thank you to everyone who stayed with me through this journey. Almost a year ago, when I started this project, I thought it would be a walk in the park, but it turned out to be the complete opposite. It was insanely expensive, time-consuming and brutally educational. Would I build it again? Right now, I'm just glad it's done. And honestly, I'm damn proud of it. So, how does it ride? Honestly, I can't really complain. It has enough power, feels safe and just works. The footpad sensor works great, and the angle is much more comfortable now. It's not a complete different board than my prototype, but it feels way more refined. For the first ride, I have both of my whippets with me, and yeah, one of them is kind of a wild card. But the board kept up, no problem. Even with all the chaos, I never felt like I'd lose control. I'm just super happy with how it turned out. To give you some numbers, the board weighs about 13 kilos, has a 4 kilowatt motor, a range of roughly 28 kilometers, and it's fast. I haven't pushed it beyond 30 kilometers per hour yet, and honestly I'm not sure I want to. If you enjoy this build, leave a comment or a like, or maybe even subscribe. Huge thanks again to JLCCNC for supporting this video. See you next time, and maybe Yuki already knows what we are building next.